Welcome to APCV 320 Computational Thinking and Doing. Today, we will talk about data abstractions. Lecture slides were adopted from Professor Henry Worshan, Applied Computing and Computer Science Program Director, who taught this class during the fall semester of 2020. In this topic, data abstractions, we will explore how data arrangements can be simulated. The subject is known as data structures in computing curricula. Data structures are ubiquitous abstractions for representing and manipulating collections of data and programs. The goal of data structures is to allow the data's user to access collections of data as abstract tools rather than force the user to think in terms of the computer's main memory organization, which is a sequence of memory cells. This topic will lead to the topic of data structures supported in Python and topic of object-oriented programming based on objects and classes. We will cover the latter topics in the following weeks. More specifically, we will cover data structure fundamentals, related concepts such as static and dynamic data structures, and implementing data structures. We will also explore a short case study on data structures. Let us check the basic data structures first. First, an array is a block of data whose entries are of the same data type. The simplest form of array is the one-dimensional array, which is a single row of elements. Each element on an array could be identified by an index, which is the position of the element on the array. For example, we can use a one-dimensional array with 26 elements. Each element could be used to store the number of times each alphabet letter appears in a page of text. For example, if the first element on the array stores the value 100, it indicates the letter A shows up 100 times in the text. A two-dimensional array consists of multiple rows and columns like a matrix. The positions of the elements are identified by pairs of indices. Each pair is composed of two index numbers. The first index identifies the row associated with the position, and the second index identifies the column. For example, we can use a rectangular array of numbers representing the monthly sales made by members of a sales force. Each entry represents a monthly sales made by a particular member. More specifically, the entry in the third row and the first column would represent the sales made by the third salesperson in January. An aggregate type is a block of data items that might be of different types and sizes. The items within the block are usually called fields. An example of an aggregate type would be the block of data relating to a single employee. The fields in an employee aggregate may include employee's name, an array of the type of character, age of type integer, and the skill rating of type of float. To access the field such as an employee's name in an aggregate type, the data access could be done by field name rather than by a numerical index number used in array data access. Another basic data structure is a list. Almost any collection of data can be envisioned as a list. For example, text can be envisioned as a list of symbols. A CD can be envisioned as a list of sounds. More common examples include guest lists, shopping lists, class student lists, and inventory lists. Lists and list operations such as add, remove, and search are common in many programs. Basic operations on collections include adding elements, removing elements, iterating over all elements, and determining whether an element is in the collection. By restricting the manner in which the entries of a list are accessed, we obtain two special types of lists known as stacks and queues. The last data structure listed on this slide is a tree. A tree is a collection whose entries have a hierarchical organization. You may not have used this data structure in your programming yet, but it's rather straightforward at the conceptual level. I will show you more details in the following slides. As I mentioned while explaining the previous slides, a list is a collection of entries that are arranged sequentially, figure 8.1a. The figure A in this slide shows a list of names. The beginning of a list is called the head of the list. The other end of the list is called the tail. A stack is a list in which entries are inserted and removed only at the head. An example is a stack of books, assuming that all additions and deletions of books happen at the top as shown in figure 8.1b. The head of a stack is called the top of the stack. The tail of the stack is called its bottom or base. Figure C shows a queue of people. An example is a line or a queue of people waiting to buy tickets at a theater, which is depicted in figure 8.1c. The person at the head of the queue is served while the new arrivals step to the rear or tail of the queue. This slide presents the terminology for lists, including a list as a collection of data whose entries are arranged sequentially, the head of a list as the beginning of the list, and the tail of the list as the end of the list. A stack is a special list that has entries removed and inserted at the head. The data structure is known as LIFO data structure, which is pronounced as L-I-E-F-O-E, which is LIFO. The top of a stack refers to the head of the list. The bottom or base of a stack refers to the tail of the list. Removing an entry from the top of a stack is called popping an entry. Inserting a new entry at the top of a stack is called pushing an entry. Note that the last entry placed on a stack will always be the first entry removed. This observation leads to the fact that a stack is known as a last in, first out, or LIFO structure. This slide shows some Python code that's used to define a stack module. At the beginning, there is a variable named stack that refers to an empty list. The method push uses the global variable stack to store the new added element to the stack. The method pop uses the global variable stack again to pop out the top element on the stack. The top method uses the stack to access the element that was the most recently added to the stack. If the stack is empty, a message is printed out and none is returned to indicate there is no value in the stack. The empty method uses not in Python to check if the stack list is empty. The member method uses an operator to check if the object is a member in the stack. The size method uses the len method to check the number of elements in the stack. The dump method uses a print method to print out the stack contents. A queue is a list in which the entries are removed only at the head and the new entries are inserted only at the tail. Essentially, a queue is a first in, first out, or FIFO structure, which means that the entries are removed from a queue in the order in which they were stored. The bottom part of the slide shows methods in a module that can simulate operations on a queue. The operations include adding an element to a queue, deleting the element at the head of the queue, retrieving the head element of the queue, retrieving the tail element if the queue is not empty. The other methods are similar to the ones that have the same names in the stack module presented in the previous slide. If you are interested, you may write the method definitions in the module to simulate a queue data structure. Now let's look at the true data structure. A tree is a collection whose entries have a hierarchical organization similar to that of an organization chart of a typical company, figure 8.2. The president is represented at the top with lines branching down to the vice presidents, who are followed by regional managers and so on. Let us check the terms used for a tree structure. A tree is a collection of data whose entries have a hierarchical organization. Each position in a tree is called a node, as shown in figure 8.3 below. The node at the top is called the root node. Notice that if we turn the drawing upside down, this node would represent the base or root of the tree. The nodes at the other extreme are called terminal nodes, or sometimes are called leaf nodes. One constraint of a tree structure is that every node except the top root node has only one parent on the structure. At times, we refer to tree structures as though each node gives birth to those nodes immediately below it. In this sense, we often speak of a node's ancestors or descendants. We refer to its immediate descendants as its children and its immediate ancestor as its parent. Moreover, we speak of nodes with the same parent as being siblings. On a tree structure, a node can have no more than one parent node. The parent node is the one immediate above the specified node. Every node on a tree has a single parent except the top root node. A child node from a specified node is a node immediately below the specified node. An ancestor node is a parent, parent of parent, etc. with respect to a specified node. A descendant node, on the other hand, is a child, child of a child, and so on with respect to a specified node. A node on a tree can have siblings, each of them is a node that share a common parent with the specified node. A tree in which parent has no more than two children is called a binary tree. The depth of a tree is the number of nodes in the longest path from root to leaf. To illustrate what's a depth of a tree, let us consider a tree that has 3 levels. The question is, what is the maximum number of tree nodes on the tree? At level 1, there is one and only one node, the root. At level 2, there are 2 nodes at most from the root. At level 3, from each node. At level 2, there are at most 2 children growing from it. Thus, there are 4 leaf nodes on the tree of depth 3. If we add the numbers together, the maximum number of tree nodes on a binary tree with depth 3 is 7. In addition to root, terminal, or leaf nodes and siblings, this slide presents one more term called subtree. If we select any node in a tree, we find that the nodes below it also have the structure of a tree. We call these smaller structures subtrees. Thus, each child node is the root of a subtree below the child's parent. Each such subtree is called a branch from the parent. In a binary tree, we often speak of a node's left branch or right branch in reference to the way the tree is displayed. An important distinction in constructing abstract data structures is whether the structure being simulated is static or dynamic. That is, whether the shape or size of the structure changes over time. For example, if the abstract tool is a list of names, it's important to consider whether the list will remain a fixed size throughout its existence or expand and shrink as names are added and deleted. As a general rule, static structures are most easily managed than dynamic ones. If a structure is static, we need merely to provide a means of accessing the various data items in the structure. Additionally, perhaps we need a means of changing the values at designated locations. On the other hand, if the structure is dynamic, we must also deal with the problem of adding and deleting entries as well as finding the memory space required by a growing data structure. In the case of a poorly designed structure, adding a single new entry could result in a massive arrangement of the structure. No matter what data structure is simulated, the various cells in a machine's main memory are always identified by numeric addresses. The numeric addresses can be encoded and stored in memory cells. A pointer is an abstracted data structure that represents a storage area where a numeric address is stored. In the case of data structures, a pointer is used to record location where data items are stored. For example, if we must repeatedly move an item of data from one location to another, we might designate a fixed location to serve as a pointer. Then each time we move the item, we can update the pointer to reflect the new address of the data. Later, when we need to access the item of data, we can find it by means of the pointer. Indeed, conceptually, the pointer will always point to the data. As an example of the application of pointers, suppose we have a list of novels stored in a computer's memory alphabetically by title. Although convenient in many applications, this arrangement makes it difficult to find all novels by a particular author. The books are scattered throughout the list. To solve this problem, we can reserve an additional memory cell with each block of cells representing a novel and use this cell as a pointer to another block representing a book by the same author. In this manner, the novels by the same author, who is Hemingway for this example, can be linked together. Once we find one novel by a given author, we can find all others by following the pointers from one book to another. For the matrix, how to store the 50 values in a memory. The expression bracket C times bracket I minus 1 bracket plus bracket J minus 1 bracket times bracket C times bracket I minus 1 bracket plus bracket J minus 1 is sometimes called the address polynomial. From this slide, we would like to investigate how the data structures are implemented. For an array data structure, such as a single-dimensional array of 20 integers, the integers can be stored in a sequence of contiguous memory cells. The cell is able to store an integer, and the array needs 20 contiguous cells to store the data. For a two-dimensional array, such as the matrix containing 5 rows, each of which has 10 columns, the data can be stored in contiguous memory cells by rows or columns. If the data is stored by rows, it's called row major order. In C-like programming languages, a two-dimensional array is stored by row major order. In Fortran, the column major order is utilized instead. An aggregate data structure can be stored in a continuous memory block, but the data fields can be stored with separate memory cells. Figure 8.5 represents the array of temperature readings stored in memory starting at address X. This slide shows an example of the technique used for storing an array of values. Suppose we want to store a sequence of 24 hourly temperature readings, each of which requires one memory cell of storage space. Moreover, suppose we want to identify these readings by their positions in the sequence. That is, we want to manipulate the sequence as though it were a one-dimensional array. To accomplish this, we can store the readings in a sequence of 24 memory cells with consecutive addresses. If the address of the first cell in the sequence is X, the location of the fourth element is addressable by X plus 3. If the array were stored starting at address X, then the entry in the third row, fourth column, would be at address X plus bracket 5 times bracket 3 minus 1 bracket plus bracket 4 minus 1 bracket, which equals to X plus 13. On this slide, a two-dimensional array matrix stored 4 rows and 5 columns of data items. If the matrix data structure is stored in row major order, the first row is stored first and the second row is stored following the previous row, and so on. Assuming each element consumes the same number of memory cells and the start address where the matrix is stored is given, we can calculate the memory address of any single element on the data structure. The value of the calculated memory address can be used to access the element in the data structure. To store an aggregate data structure such as an employee that has 3 data fields, name of type character array, age of type integer, and the skill rating of type float. If the number of memory cells required by each field is fixed, then we can store the aggregate in a block of contiguous cells. For example, suppose the field name required at most 25 cells, age required only 1 cell, and the skill rating required only 1 cell. Then we could set aside a block of 27 contiguous cells, store the name in the first 25 cells, store the age in the 26th cell, and store the skill rating in the last cell as shown in figure 8.7a. With this arrangement, it would be easy to access the different fields within the aggregate. A reference to a field can be translated to a memory cell by knowing the address where the aggregate begins and the offset of the desired field within that aggregate. An alternative to storing an aggregate in a block of contiguous memory cells is to store each field in a separate location and then link them together by means of pointers. More precisely, if the aggregate contains 3 fields, then we find a place in memory to store 3 pointers, each of which points to one of the fields, as shown in figure 8.7b. If these pointers are stored in a block starting at address X, then the first field can be found by following the pointer stored at location X. The second field can be found by following the pointer at location X plus 1, and so forth. This arrangement is especially useful in those cases in which the size of the aggregates field is dynamic. For instance, by using the pointer system, the size of the first field can be increased merely by finding an area in memory to hold the larger field and then adjusting the appropriate pointer to point to the new location. But if the aggregate were stored in a contiguous block, the entire structure would have to be altered. Let us now consider techniques for storing a list in a computer's main memory. One strategy is to store the entire list in a single block of memory cells with consecutive addresses. The same strategy we discussed to store an array. For example, if we want to store a list of names, assuming that each name is no longer than 8 letters, we can divide the large block of cells into a collection of sub-blocks, each containing 8 cells. Into each subblock, we can store a name by recording its ASCII code using 1 cell per letter. If the name alone does not fill all the cells in the subblock allocated to it, we can merely fill the remaining cells with the ASCII code for a space. Using this system would require a block of 80 consecutive memory cells to store a list of 10 names. A contiguous list is a convenient storage structure for implementing static lists, but it has disadvantages in the case of dynamic lists, in which the deletion and insertion of names can lead to a time-consuming shuffling of entries. The problems can be mitigated if we allow the individual entries in a list to be stored in different areas of memory rather than together in one large contiguous block. To keep track of the beginning of a linked list, we set aside another pointer in which we save the address for the first entry. Since this pointer points to the beginning or head of the list, it's called the head pointer. To mark the end of a linked list, we use a null pointer, also known as a NIL pointer in some languages, or the none object in Python, which is merely a special bit pattern placed in the pointer cell of the last entry to indicate that no further entries are in the list. For example, if we agree never to store a list entry at address 0, the value 0 will never appear as a legitimate pointer value and can therefore be used as the null pointer. This slide presents how to use a contiguous list to implement static lists. You have to be aware that this approach has disadvantages in the case of dynamic lists, where the deletion and insertion of names can lead to a time-consuming shuffling of entries. In a worst-case scenario, the addition of entries could create the need to move the entire list to a new location to obtain an available block of cells large enough for the expanded list, since it needs continuous memory cells to contain the names. To mark the end of a linked list, we use a nil pointer, also known as a null pointer, which is merely a special bit pattern placed in the pointer cell of the last entry to indicate that no further entries are in the list. A linked list approach could be better than a contiguous list when dealing with dynamic lists. To explain, let us reconsider our example of storing a list of names where each name is no more than 8 characters long. This time, we store each name in a block of 9 contiguous memory cells. The first 8 of these cells are used to hold the name itself, and the last cell is used as a pointer to the next name in the list. Following this lead, the list can be scattered among several small 9 cell blocks linked together by pointers. Because of this linkage system, such an organization is called a linked list. Again, to keep track of the beginning of the linked list, we have another pointer, the head pointer, which points to the beginning of the list. The final linked list structure is represented in figure 8.9. The figure depicts the scattered blocks of memory used for the list by individual rectangles. Each rectangle is labeled to indicate its composition. Each pointer is represented by an arrow that leads from the pointer itself to the pointer's addressee. Traversing the list involves following the head pointer to find the first entry. From there, we follow the pointers stored with the entries to hop from one entry to the next until the null pointer is reached. In a contiguous list, deleting an entry from a linked list would create a hole, meaning that those entries following the deleted one would have to be moved forward to keep the list contiguous. However, in the case of a linked list, an entry can be deleted by changing a single pointer. To appreciate the advantages of a linked list over a contiguous one, consider the task of deleting an entry. In a contiguous list, this would create a hole, meaning that those entries following the deleted one would have to be moved forward to keep the list contiguous. However, in the case of a linked list, an entry can be deleted by changing a single pointer. This is done by changing the pointer that formerly pointed to the deleted entry so that it points to the entry following the deleted entry, as shown in figure 8.10. From then on, when the list is traversed, the deleted entry is passed by because it no longer is part of the chain. Inserting a new entry in a linked list is only a little more than manipulating pointers. To insert an entry for a new name, we first find an unused block of memory cells that's large enough to hold the new name and a pointer. After the memory is determined for the new name entry, we store the new name and fill in the pointer with the address of the entry in the list that should follow the new entry. Finally, we change the pointer associated with the entry that should precede the new entry in the list so that the preceding entry's pointer points to the new entry as shown in figure 8.11. After we make this change, the new entry will be found in the proper place each time the list is traversed. For storing stacks and queues, an organization similar to a contiguous list is often used. In the case of a stack, a block of memory large enough to accommodate the stack as its maximum size is reserved. Note that it could be tricky to determine the size of the stack block. If too little room is reserved, the stack will ultimately exceed the allocated storage space. However, if too much room is reserved, memory space will be wasted. Stack is LIFO data structure. To push a new entry on the stack, we first adjust the stack pointer to point to the vacancy just beyond the top of the stack and then place the new entry at this location. To pop an entry from the stack, we read the data pointed to by the stack pointer and then adjust the stack pointer to point to the next entry down on the stack. When applying contiguous memory block to a stack, one end of this block is designated as the stack's base. Above the base, there is space for the first entry to be pushed onto the stack. Then each additional entry is placed next to its predecessor as the stack grows towards the other end of the reserved block. Observe that as entries are pushed and popped, the location of the top of the stack will move back and forth within the reserved block of memory cells. To keep track of this location, its address is stored in an additional memory cell known as the stack pointer. You might have heard the term stack pointer before. Essentially, the stack pointer is a pointer to the top of the stack. Note that queue is a FIFO data structure. A problem with the storage system for a queue, as entries are inserted and removed, the queue crawls through memory like a glacier. The traditional implementation of a queue is similar to that of a stack. Again, we reserve a contiguous block that's sufficiently large to hold the queue data as its projected maximum size. To support performing operations on the queue data, we set aside head pointer and tail pointer, which are stored in two memory cells. The head pointer keeps track of the head of the queue. The tail pointer keeps track of the tail. When the queue is empty, both of these pointers point to the same location as shown in figure 8.13. Each time an entry is inserted into the queue, it's placed in the location pointed to by the tail pointer, and then the tail pointer is adjusted to point to the next unused location. In this manner, the tail pointer is always pointing to the first vacancy at the tail of the queue. Removing an entry from the queue involves extracting the entry pointed to by the head pointer and then adjusting the head pointer to point to the next entry in the queue. A problem with the storage system used to store queue data is that as entries are inserted and removed, the queue crawls through memory like a glacier, moves slowly. See again figure 8.13. Thus, we need a mechanism for confining the queue to its reserved block of memory. Here is the solution. The idea is to let the queue migrate through the block. When the tail of the queue reaches the end of the block, we start inserting additional entries back at the original beginning of the block, which by this time is vacant. Likewise, when the head pointer points to the last entry in the block, a delete operation removes this entry and adjusts the head pointer back to the beginning of the block where other entries are by this time waiting. In this manner, the queue chases itself around within the block as though the ends of the block were connected to form a loop. The result is an implementation called a circular queue. For the purpose of discussing tree storage techniques, we restrict our study to binary trees. As mentioned before, binary trees are trees in which each node has at most 2 children. Such trees normally are stored in memory using a linked structure similar to that of linked lists. On the linked structure, entry node contains 3 components. Number 1, the data. Number 2, a pointer to the node's first child. And number 3, a pointer to the node's second child. The tree is accessible by a pointer points to the root node on the tree. A tree can also be stored using a continuous array structure. In one of the previous slides, we studied how to calculate the maximum number of nodes on a binary tree given the depth of the tree. For example, a binary tree of depth 3 could have at most 7 nodes. To store the data items on a binary tree of depth 3, we can use contiguous memory block that has capacity to store the maximum number of nodes on the tree. Although there is no left or right inside a machine, it's helpful to refer to the first pointer as the left child pointer and the other pointer as the right child pointer in reference to the way we would draw the tree on paper. Thus, each node of the tree is represented by a short contiguous block of memory cells with the format shown in figure 8.15. The arrows are illustrating the semantic meaning of the encoded addresses represented by the pointers. Following the address, we can locate the data referred by the pointer. Figure 8.16 presents a binary tree example with this linked storage system. The conceptual binary tree structure is exhibited along with a representation of how that tree might actually appear in a computer's memory. Note that the actual arrangements of the nodes within the main memory might be quite different from the conceptual arrangement. However, by following the root pointer, we can find the root node and then trace any path down the tree by following the appropriate pointers from node to node. An alternative to storing a binary tree as a linked structure is to use a single contiguous block of memory cells for the entire tree. For simplicity, we assume that each node of the tree requires only 1 memory cell. Using this approach, we store the tree's root node in the first cell of the block. Then we store the left child of the root in the second cell, store the right child of the root in the third cell, and so on. In general, the left and right children of the node found in cell n are stored in the cells 2n and 2n plus 1 respectively. By this approach, some cells, such as cell 6, is marked as absence of data. Using this approach for a sparse, unbalanced binary tree, a lot of cells would be marked as data absence. For example, there are only 5 data items in the tree structure, but the tree structure needs to reserve 15 cells considering there are up to 15 items in a tree of depth of 4. Thus, this approach potentially leads to wasted space. We have seen that the way data structures are actually stored in a computer's memory is not the same as the conceptual structure envisioned by the user. A 2-dimensional array is not actually stored as a 2-dimensional rectangular block, and a list or a tree might actually consist of small pieces scattered over a large area of memory. Hence, to allow the user to access the structure as an abstract tool, we must shield the user from the complexities of the actual storage system. In the case of lists, stacks, queues, and trees, instructions stated in terms of the abstract structure are usually converted into the appropriate actions by means of functions that manipulate data in the data structures while shielding the user from the details of the underlying storage system. For example, a stack data structure can be operated by push and pop procedures. The data structure or the data structures as well as the procedures from an abstraction for us to create, manage, and process data. Figure 8.19 presents a procedure named print list for printing a linked list of names. This procedure assumes that the input is a list of items. The procedure body uses a current pointer points to the first entry of the list. Each entry in the list consists of two pieces, a name and a pointer to the next entry. The while statement is a loop used to iterate over each item on the list. In the look iteration body, the print statement prints the value stored in each item. After the print statement, the current pointer is adjusted pointing to the next entry on the list. The loop stops when the current pointer completes the iteration pointing to nothing. Once this procedure has been developed, it can be used to print a linked list as an abstract tool without being concerned for the steps actually required to print the list. For example, to obtain a printed class list for this class, I will need only call this procedure with the list of enrolled students. The procedure can print out the item values as desired list. Let us consider the task of storing a list of names in alphabetical order. We assume that the operations to be performed in this list include search, print, and insert. Search is used for the presence of an entry, print is for displaying the list in alphabetical order, and insert is used for adding a new entry. Our goal is to develop a storage system along with a collection of functions to perform these operations, thus producing a complete abstract tool. What's your plan to store the names? Our solution is to store the list as a binary tree. We make the middle list entry the root node. Then we make the middle of the remaining first half of the list the root's left child, and we make the middle of the remaining second half the root's right child. The middle entries of each remaining fourth of the list become the child of the root's children, and so forth. For example, the tree in figure 820 represents the list of letters A, B, C, D, E, F, G, H, I, J, K, L, and M. We consider the larger of the middle two entries as the middle when the part of the list in the question contains an even number of entries. To search the list stored in this manner, we compare the target value to the root node. If the two are equal, our search has succeeded. If they are not equal, we move to the left or right child of the root, depending on whether the target is less than or greater than the root, respectively. There we find the middle of the portion of the list that's necessary to continue the search. This process, comparing and moving to a child, continues until we find the target value, meaning that our search was successful. Or we reach a null pointer, which is none, without finding the target value, meaning that our search was a failure. Large cosmetic, instead of stating the algorithm in terms of searching successively smaller segments of the list, we now state the algorithm in terms of searching successively smaller subtrees, as shown in figure 8.22. Having stored our list as a binary tree, you might think that the process of printing the list in alphabetical order would now be difficult. However, to print the list in alphabetical order, we merely need to print the left subtree in alphabetical order, print the root node, and then print the right subtree in alphabetical order, as shown in figure 8.23. After all, the left subtree contains all the elements that are less than the root node, while the right subtree contains all the elements that are greater than the root. A sketch of our logic so far looks like this. This outline involves the tasks of printing the left subtree and the right subtree in alphabetical order, both of which are essentially smaller versions of our original task. That is, solving the problem of printing a tree involves the smaller task of printing subtrees, which suggests a recursive approach to our tree printing problem. Following this lead, we can expand our initial idea into a complete Python function for printing our tree as shown in figure 8.24. We have assigned the function the name print tree and then requested the service of a print tree for printing the left and right subtrees. Note that the termination condition of the recursive process reaching a null subtree or none is guaranteed to be reached because each successive activation of the function operates on a smaller tree than the one causing the activation. The task of inserting a new entry in the tree is also easier than it might appear at first. First, we need to find the proper place for a new entry. To accomplish this, we move down the tree along the path that we would follow if we were searching for that entry. Since the entry is not in the tree, our search will lead to a null pointer. At this point, we will have found the proper location for the new node. Indeed, this is the location to which a search for the new entry would lead. Figure 8.25 shows the two steps for an insertion example. First, M is searched and the right child of K is reached out. Since the pointer is empty, M can be added as an additional node to the tree. A function expressing this process in the case of a linked tree structure is shown in figure 8.26. It searches the tree for the value being inserted, called a new value, and then places a new leaf node containing a new value at the proper location. Note that if the entry being inserted is actually found in the tree during the search, no insertion is made. The Python code in figure 8.26 uses the function call tree node to create a new aggregate to serve as a fresh leaf in the linked tree structure. This requires additional code outside of the figure to identify tree node as user-defined type, as we will see in the next section. So that wraps up this lecture. I know that was rather fast kind of going through it. Some of the slides you may need to review in more details as they require another pass through. So this concludes the lecture, and certainly you can email me questions if you did not get the chance to watch the live lecture. That was a lot to go through and digest. We will revisit many of these concepts later in the course during the following lectures, which will include additional reading reference materials. And in the next module, we will explore data abstractions in Python.